Okay, in the previous lecture, we considered single phase half wave rectifier, and we have seen how we can analyze the circuit, how we can find out the current expression under different load conditions. We also discussed that what happens to the energy flow, power flow in different segments of the load current. If you recall, when the current is of increasing nature, the source is feeding power to the load, and during this period resistance is consuming power and inductor is also storing the energy in its magnetic field. From the peak of the current till the zero crossing point of the supply voltage, source is feeding power to the load and inductor releases its stored energy, and the complete power goes to the resistance. And beyond that zero crossing point, the inductor releases its rest of the stored energy. Part of that goes to the resistance and rest goes back to the source. Now this can be used to understand how the freewheeling diode improves the input power factor. But before we consider the input power factor, let us consider some of the performance parameters of converters, and on the basis of these performance parameters we can see whether a converter is better or not. Now, to understand the performance parameters, if you recall the load current, with resistive load the current was like this, and with inductive load the current was like this. None of the current is sinusoidal, none of the current is DC, and since the circuit is like this, so whatever is the load current, same is the current coming from the source. This current is having all sort of components, DC component plus all harmonics. We can represent this source current like this. It is having a DC component plus it is having all harmonics. Just to say it is the DC current in the source, I am putting a suffix S also. So the source current is having DC component plus all harmonics. These are the RMS values of the RMS of nth harmonic component. This is the phase angle of the nth harmonic component. But as far as voltage is concerned, voltage is sinusoidal, so it is root 2 Vs1 sine of omega t. It doesn't have any harmonics, only fundamental component is there. If you want to find out how much power is coming from the source, it is the source voltage into the source current. This voltage into this current. And if you find out how much average power is coming from the source, it is 1 upon 2 pi, 0 to 2 pi, instantaneous power d omega t. Now if you multiply this voltage with this current and integrate from 0 to 2 pi, it will be 0. If you multiply sin omega t with different terms, all terms will give you 0 value, average value, but only one component for which n is equal to 1, you will get non-zero value. Remember, sin omega t into just remember this expression, sin m theta into sin n theta. If you integrate over a period, it will be 0 if m is not equal to n. So if it is sin 2 omega t, 3 omega t, 4 omega t, multiply by sin omega t and find out the average, it will come out to be 0. But if it is sin omega t, that is the fundamental component, sin omega t minus phi 1 into sin omega t, that gives you non-zero value, and its resultant will be RMS value of the fundamental voltage, RMS value of the fundamental current, cos of phi 1, Vi cos phi, that is the average power. This average power, you can notice, is only due to fundamental current. It means only the fundamental current is responsible for the active power flow from the source to the load. Rest of the components, they are harmonics, they are not contributing to any average power flow, and the reason is the source voltage is basically sinusoidal and it is having only fundamental component. This is one point which we should keep in, that only fundamental load current is responsible for the active power flow. We can also say that if this is the source current, its RMS value is the RMS value of all component is square or you can say it is IS1 is square. I am taking this component here plus ISN is square summation and not equal to 1 to infinity 0, 2, 4, 6, all components put together, that is. You may also say this is the distortion component, because all components which are not contributing to the power flow, they are basically the distortion in the input current. So all these components we can say like this. Now there is one way of expressing the distortion, and that is in terms of THD, total harmonic distortion. Total harmonic distortion is defined as the ratio of I distortion to I fundamental. You can also put it like this: I distortion is square upon IS1 is square. You can also put it like this. I distortion is basically IS square minus IS1 square. This is the RMS value of the overall current, and these are the RMS values of the individual components. This can be written as IS upon IS1 square minus 1. So you can say IS upon IS1 is 1 plus THD square. Or you can say IS1 upon IS1 upon IS square root of this. IS1 upon IS is 1 upon 1 plus THD square. This IS1 upon IS is basically called distortion factor dF. Distortion factor dF. Then, how the power factor is defined? Normally we say power factor is cos of phi, but that is the case when voltage and the currents all are sinusoidal. Here you have sinusoidal voltage, but the current is non-sinusoidal, and that's why the power factor is defined basic definition remains same, and that is active power output upon RMS power input, or you can say apparent power input. Since the converter is assumed to be a lossless, active power output is same as active power input and divided by RMS power input. Just now we have seen active power input is fundamental voltage, fundamental current, fundamental power factor, and the RMS power input is the RMS value of the source voltage, RMS value of the source current. Since input voltage is sinusoidal, so RMS value of the source voltage is same as RMS value of the fundamental voltage. This cancels with this one. It becomes IS1 upon IS times cos of phi 1. So you can say that input power factor IS1 upon IS is distortion factor into cos phi 1, which is called input displacement factor, or you can say fundamental power factor. So the input power factor is a product of distortion factor and input displacement factor. If voltage and the current both are sinusoidal, then what happens to distortion factor? Because IS and IS1 both are same, and therefore the distortion factor becomes unity. No distortion in the current. Input displacement factor remains cos of phi 1, and therefore input power factor is same as input displacement factor, that is cos of phi 1. Ideal condition. But when there is a distortion, then the input power factor becomes poorer, and that is because of the distortion in the current waveform. So whenever you are finding the input power factor of any converter, you have to keep in mind these two things, distortion factor and the input displacement factor, and the distortion factor is also given in terms of total harmonic distortion, that is 1 upon square root of 1 plus THD square. Now let us see how the freewheeling diode improves the input power factor. We normally say by connecting a freewheeling diode across the load, the power factor gets improved. Mathematically we can prove, but physically we can also explain. This is the circuit, and here you have connected a freewheeling diode. This is the thyristor, input voltage, and this is the load. This is the load current. Now so far we have considered the circuits where you have only one switching device, SCR, and therefore it is very easy to find out whether that device is forward bias or reverse bias. We have seen how we can find out that. But if there are multiple devices like this, uncontrolled, semi-controlled like this, you have to first see which device is forward bias, which device will go into conduction. One thing you can always remember from the previous knowledge, that whenever the devices are connected, either their cathodes are common or their anodes are common, right? Now to analyze this circuit, let us consider a simple example of, say, 3 diodes connected like this, and then you have a load, and say the voltages are say this is 10 volt, this is say 15 volt, and this is say 20 volt, and these are the diodes D1, D2 and D3. If I ask you what will be the output voltage, say in online mode I cannot ask you, but some may say 10, some may say 50, some may say 20, some may say average of the voltages and so on. But if you look, if I remove this portion, you can say the output voltage will be 10 volt. If I remove this portion, you will see output voltage will be 15 volt. And if I remove this portion, you will see output voltage will be 20 volt. What will be the output voltage? It cannot be 10, 15 or 20 all. It has to be only a single voltage. What happens? Out of these diodes, which are in common cathode mode, the diode which is maximum forward bias will conduct. If you see, this diode is maximum forward bias 20 volt and this will conduct, and the moment this diode conducts, this voltage will become 20 volt, and when this becomes 20 volt, this diode is reverse biased by 5 volt, this diode is reverse biased by 10 volt, and therefore D1 and D2 they stops conducting, they will not conduct rather, and D3 will conduct, making the output voltage 20 volt. So if there are several devices connected in a common cathode mode like this, the device which is maximum forward bias will conduct and then reverse biases rest of the devices. If you look this particular circuit, I can redraw this circuit in the same manner. This is the freewheeling diode and this is the SC. You can say there is no biasing voltage for this diode, but there is a biasing voltage for this SCR. It means in the positive half cycle of input voltage, this is forward bias, but this is not biased by any voltage. So out of the two, this is more forward bias than this, and therefore it can go into conduction. If I see the voltage and the current waveform, this is the input voltage. In the positive half cycle, this is basically forward bias and this is not biased, right in the very first cycle I am talking about. And therefore, you can trigger this SCR. Like previous case, you can trigger it at a firing angle alpha by giving a short duration pulse. The moment signal is applied, device goes into conduction, making the output voltage same as input voltage, and this particular diode will be reverse biased. Since it is inductive circuit, so there will be a current flow like this. And if you recall the current expression which we derived in the previous class, it means current increases and then decreases, right? Now when the current is of increasing nature, there is a drop across the resistance, there is a voltage across the inductance, and inductor stores the energy. No change. From peak value till this particular point, what happens? Current is of decreasing nature, and because of that, the inductor voltage polarity has reversed. LdI naught upon dt becomes negative. Now if you look this particular voltage polarity and you move around this loop, this plus it is forward biasing the diode. This voltage is also forward biasing the thyristor. When there is no freewheeling diode, inductor voltage basically helps in forward biasing it more and the current continues to flow. In the case of diode also, this inductor voltage, you can say it is forward biasing this freewheeling diode, it is also forward biasing this SCR equally. But input voltage is still positive, it means this voltage is still forward biasing this SCR. Net result is this SCR is getting more forward bias than this diode, and since SCR is in conduction, therefore it continues to conduct even beyond peak value. And as long as this device is in conduction, this voltage appears across the load, making this freewheeling diode reverse bias. So the output voltage will be like this. Up to this point there is no change. And what happens from peak to this point? Inductor releases its energy, which will also go to the resistance. Source is also feeding the power, that is also consumed by the resistance. No change. But what happens beyond pi? Beyond pi, now input voltage has become negative. It means this is now reverse biasing SCR. Inductor voltage is forward biasing this, it is forward biasing SCR. What is the net result? This is less forward bias than the freewheeling diode, because for this only forward bias is available, but for this is the reverse bias. It means beyond pi, freewheeling diode is more forward biased than SCR, and diode doesn't need any triggering pulse. It means just after this point, this diode will go into conduction. The current which was earlier flowing through this will now be stopped. Current transfers to this particular device and freewheeling action takes place. Commutation of thyristor takes place. It is the transfer of current from outgoing device to the incoming device. That is what we say is the commutation. Transfer of current from outgoing to incoming device. Current is now freewheeling in this loop. And when the diode conducts, this point the voltage is 0. The input voltage directly appears across SCR, making it reverse bias, and it stops conducting. During this period, this expression is no longer true. This is true only from and at this particular point, let us say it is having a value I naught at pi. When the freewheeling action takes place, then the current decreases and becomes 0. What will be the nature of this current? You can again find out the expression in an identical manner. That from omega t greater than pi, this instant let us say it omega t double dash 0. What will be the equation? Output voltage is 0. It is R I naught plus L d I naught upon dt. Circuit is reduced to we can again find out the current expression in the same manner. there will be one steady state current plus one transient current. In this case, the steady state current will be 0. And the transient current we do not know. We can say it is A dash e raised to minus t double dash by tau. At this particular instant, when the switching takes place, the current will be maximum. Transient current will be maximum, and then it decays exponentially with the time constant of the circuit. I have used the proper suffixing like this because in the previous case we used A and T dash, now it is A dash and T double dash. So the total current is this. How to find out this? From the initial condition at T double dash equals to 0, that is omega t equals to pi, the current is basically I naught at pi. So if you put it here, A dash you know, so I naught is I naught at pi e raised to minus t double dash by tau, or you can say I naught at pi e raised to omega t minus pi upon omega tau. This omega t double dash upon omega tau, omega t double dash is basically omega t minus pi. This will be the exponentially decaying current, and during this period output voltage is 0, and after that also output voltage will be 0. Now the question is, waveforms are fine, but how the input power factor has improved? Now what has happened? Up to pi we have seen that 0 to theta inductor has stored the energy. From theta to pi inductor has released the energy which goes to the resistance. Beyond pi, inductor releases its rest of the stored energy. If you do not have a freewheeling diode, part of the energy will be consumed here, but rest will go back to the source. But if there is a freewheeling, it means the entire energy released by the inductance is consumed by the resistance. What you can say, the active power output has become more, and by definition input power factor is active power output upon RMS power input. Active power output has increased, that improves the input power factor. Physically you can explain it like this. Mathematically we'll see later on when the waveforms are easy to be analyzed that how much improvement is there in the power factor. But effect of freewheeling diode is to improve the input power factor, and it improves it in this manner. You can find out the average output voltage expression integrating this one from alpha to pi and so on. This